This is EC 201, lecture 46. So the last time around, we were looking at simple applications of op-amps. So we derived the inverting amplifier, the non-inverting amplifier, the summing amplifier, and we just started off with an integrator. You should never operate an operational amplifier without any DC negative feedback around it. Okay. So an integrator operating open loop in a practical situation will result in the output of the op-amp being either hitting the positive or the negative rail depending on the sign of the offset delta V. And once it hits the positive or negative rail, the devices are all saturated or cut off, so the incremental gain of the amplifier is no longer the infinity that you thought it was. The entire assumption that inverting terminal of the op-amp and the non-inverting terminal of the op-amp are the same potential, all that is bust now. So to continue on to the next topic, as I said, the preliminary motivation for a lot of the early op-amp work was to use the op-amp in circuits to get rid of inductors. The reason why you need large inductors in those days was the fact that you're targeting a telephone system and you need to basically filter off the input signal beyond about 4 kilohertz. Let's first see one way of emulating or simulating an inductor, or trying to make the input impedance of a black box look as if there was an inductor inside the black box without actually having one. Okay. For this we will try and use the stuff that we know already, which is the Miller effect. What did we say? If we had an amplifier of this sort with a gain A, so if this was Vi and this was Vo and Vo was A times Vi, then if we put a resistor between the input and the output, what is the input impedance looking in here? This is Vi, this is A times Vi. So what is the voltage across the resistor? The voltage across the resistor is Vi minus A times Vi. So the current flowing through the resistor must be Vi minus A times Vi divided by R. That current must be flowing like this, which must be coming from the input here. Okay. And if you assume that this is a voltage controlled voltage source, then the current flowing here is 0. So the total current being drawn from the input source is, so Zn is nothing but the voltage you applied divided by the current that's drawn from the source, and the current that's drawn from the source is nothing but Vi times 1 minus A divided by R, which means the input impedance looking in is R divided by 1 minus A. Simple enough. So we want Zin to look like an inductor which means we want Zin to be of the form J omega L or S times L. If we want Zin to be S times L, what should A be? SL must be R divided by 1 minus A, which means A minus 1 must be minus R by SL, or A must be equal to 1 minus R by SL. So all that this is saying is that if I had a voltage controlled voltage source with a frequency dependent gain of this form, that is A was equal to 1 minus R by SL, then if I connect a resistor between the input and output of this VCVS, then the looking in impedance will look like an inductor of value L. Is that clear? So now the job reduces to finding or designing a voltage controlled voltage source with a frequency response of this nature. In other words, we want A of S to be 1 minus R by SL. We already know one trick, and what is the trick that we learned? We know that if one can synthesize a transfer function H1, then 1 minus H1 can be easily got by interchanging input and ground. So in other words, instead of trying to attack the problem of finding 1 minus R by SL, I can start by trying to design something with a transfer function A1 of S, which is R by SL. Okay? You understand? So what kind of transfer function is this? What does this remind you of? This is what kind of mathematical operation? 1 over S is integration. So basically what you need is, this is nothing but a non-inverting integrator. Right? Do we know how to realize an integrator? The integrator is quite straightforward. R, C, if this is Vi, what is the voltage here at the output of the op-amp? Minus Vi times SCR. So this is what kind of integrator? Is it inverting or non-inverting? It's an inverting integrator. You want a non-inverting integrator, so you must multiply this with a gain of minus 1. So can you suggest a way in which I can multiply this by minus 1? And one way of doing it is to cascade this with a gain of minus 1, and that's obtained by doing this. So the voltage here will be plus Vi by SCR. Now if I want 1 minus 1 by SCR, what should I do? Interchange input and ground. So whatever was the input must now become ground. Whatever was ground must now become the input. So there were two grounds here. By our theory, what must the output be? 1 minus SCR times VI. Does it make sense? Now, so what is the rest of the story? What must I do? We said that if you had an amplifier with a gain A of S, which is of the form 1 minus R by SL, then connecting a resistor between the input and output of the VCVS should give you an inductor looking in. So this is the input of the VCVS, this is the output. So what should I do now? Connect a resistor between the two. And the looking in impedance here should be what now? What was this? This was Vn times 1 minus 1 by SCR. So what is Zn? It is SCR square. This is the value of the equivalent inductance realized. So in other words, if I put this contraption in a black box, you would not be able to distinguish it from a grounded inductor of value CR square. Just to remove any of disbelief you may have that this actually works, let me just work out the impedance looking in, assuming that I saw the circuit. So let's do the maths. This is Vin, all these are ideal op amps. What is this voltage? This is Vin. What is this voltage? Okay. This is Vin because the op amp two input terminals must be at the same potential as long as the op amp is in a negative feedback loop. What is this current? Vn by R. So what is this current? This is also Vn by R. What is this voltage? It is Vn plus Vn by SCR. So what is this current now? Vn by SCR square. Okay. What is this current? Vn by SCR square. And when I copied, I forgot to put in this resistor here. Let's observe these two resistors. The voltage across both the resistors is this potential is the same as this potential. This potential is common to both the resistors. So if a current Vn by SCR square flows here, what can you say about the current through this resistor? Is the same thing flowing in the same direction. So this current must also be Vn by SCR square. And where does that current have to come from? This must come from here because the currents going in here and here are both 0. So the total current going in is nothing but Vn by, so if a voltage Vn is applied here, the current going in is Vn by SCR square. which means that the input impedance is nothing but SCR square. Another circuit can be simply derived by following artifice, which is we realize the non-inverting integrator by having first an inverting integrator and then an inverter. I could have done the opposite thing. So I could have the -1 amplifier first and the integrator, and then go through the same logic, and I will get another circuit diagram which looks different. Okay, but also gives you SCR square. The number of ways in which you can realize an inductor are infinite. The nice thing about this is that to get a large inductance, what do you need? You need a large resistor. Even if you have a small capacitance, the inductance value you get is proportional to R square. So with large resistors, you can get a large inductance. This shows that it is possible using op amps and resistors and capacitors to realize an inductor. In the beginning it kind of seems a little surprising, but you know that it's not really that great a thing, because you already saw how we can use control sources and make some impedance Z look like some other impedance based on what the nature of the control source is. All that we have done here is figure out the precise nature of the control source needed so that the looking in impedance looks like a pure inductor. So once you have a grounded inductor, you can do a lot of cool things. For example, if I wanted to build a band pass filter, what is the simplest example of a second order band pass filter that you can think of using L, C and R? What kind of filter is this? What is the order of the filter? First order. What kind of filter is this? Low pass filter. Now why is it low pass? Because at low frequency the capacitor is open, so VO will be equal to VI. At high frequency the capacitor is short, so VO will be equal to 0. So this network is partial to low frequencies and attenuates high frequencies. What about what is the order? It's a second order. And what kind of filter is this? DC, the capacitor is open, the inductor is short. At low frequencies, basically, this path is a short, this path is an open, and at high frequencies, this path is open and this path is a short. So this is also a low pass filter, the second order low pass filter. Now, if I wanted a second order band pass filter, what should I do? This is L, this is C, and clearly this is the second order. And why is this band pass? This shunt arm here is short circuit for DC because the inductor becomes a short circuit for very high frequencies because the capacitor becomes a short. At radian frequency of 1 over square root LC, this arm becomes, it's an open circuit. At radian frequency of 1 over LC, this LC is an open, tank is an open circuit. VO will be the same as VI. At low frequency or high frequency, the output is a short. So, this network selectively allows frequencies in and around the resonant frequency of the LC circuit to pass through and attenuates all the other frequencies. Way in which you could realize the second order band pass filter is to take our inductor and put a capacitor here, C1 let's say, and this is Vi, this is R, and this will give me what? It will give me a second order band pass response, simply because all that I have done is replace the inductor by what is called a simulated inductor or an active inductor. And so this is one application where you have a band pass filter with a very low resonant frequency can be realized without using bulky real inductors. You can get away by using only op amps which have only transistors in them, which are small, and R's and C's. So this is a second order band pass response. So since we are on the subject of filters, so when you have a frequency selective network, the basic aim is to select a band of frequencies, omega or frequency. This is the magnitude response of the network. So this band of frequencies which is let through is called the pass band, and this is the stop band. This is a low pass filter. Similarly, the ideal desired characteristic of a filter like this is a band pass filter. What about this? This is a high pass filter. And what is this? Band stop. Or sometimes called a notch filter. Okay. So if you look at first order systems, this is an example of a first order low pass. What about a first order high pass? Alright. With first order, it turns out you cannot realize a band pass characteristic. It's actually pretty straightforward to see that. I leave that to you as an exercise. This is an example of a second order low pass. Okay, what should I do to make it a high pass? This is a second order high pass. What about second order band pass? We've already seen it just now. And what is this? If I want to do a second order band stop, what would I do? what should I put here to make it a second order band stop? So basically the output should become 0 for a certain frequency. So this arm must become a short circuit for a certain frequency, which means that I can replace this by a second order, LC series band stop. Okay. And as I said, the general form of a second order section is given by h of s, which is the numerator divided by a second order denominator, which is of the form s square by omega p square plus s by omega p qp plus 1. And if the numerator is a constant, the zeros of the transfer function are at infinity, so there are no finite zeros. So this is often called an all-pole filter, which means that h of s is of the form, without laws of generality, I simply take a constant to be 1. So the form s square by omega p square plus s by omega p qp plus 1. Does it make sense? Now, let's see what happens to the magnitude of this transfer function. What is mod h of j omega the whole square? So this is an example of a simple second order low pass transfer function. In the filter parlance, it's a second order low pass filter, and to be more specific, is a second order all pole low pass filter. So what is the magnitude response? It's 1 by 1 minus omega square by omega p square the whole square plus omega square by omega p square qp square. So if I plot omega by omega p on the x-axis and mod h square on the y-axis at omega by omega p equal to 0, what is mod h? 1. So that's here. Now, for small omega by omega p, mod h of j omega square is approximately equal to the magnitude squared transfer function. The denominator will be a polynomial in omega by omega p the whole square. Why? Because the magnitude response is a even function of frequency. So the denominator polynomial of mod h of j omega the whole square must be an even function of omega by omega p the whole square. So if I expand this out, what all powers will I get? I will get a term of the form omega square by omega p square. I will also get a term of the form omega by omega p whole to the power 4. So for small values of omega by omega p, I will be able to neglect the fourth power in comparison to the second power. So this must be 1 plus 1 by qp square minus minus 2 times omega square by omega p square. Is that understood? So for small omega by omega p square. This is the approximation for the squared magnitude, and small omega by omega p is basically means for if this is 1, then it means for regions around here. 1 by qp square minus 2 is negative. Then what can you say about mod h of j omega square? It will increase around 0. Is that clear? So if this term is negative, then as I increase omega square by omega p square, the denominator becomes smaller. 1 over the denominator must get larger. So what I will see will be a transfer function like this. On the other hand, if 1 over qp square minus 2 is positive, what can you say? Mod h of j omega square will decrease around omega by omega p equal to 0. This corresponds to a qp. If 1 by qp square minus 2 is negative, what can you say about qp itself? qp is greater than 1 by root 2. This corresponds to a qp of value less than 1 by root 2. At qp is equal to 1 over root 2, what happens? It remains flat. Does that make sense? Alright. For large omega by omega p square, what must happen to the responses? They must stop. Whatever the value of q is for large omega by omega p square, they must all fall off with frequency. Whatever these guys were initially, they must do this. Alright? Let me. Okay, they'll go to 0 only at omega by omega p tending to infinity. So they must curve that way. Similarly, even if this jumped up initially, it must eventually do this. And even if qp was less than 1 over root 2, it must eventually do this. Does it make sense? So by varying the value of qp, you can make the filter response peak, you can make it flat, or you can make it droop. And the value of qp required to make the response flat, qp equals 1 over root 2, will make the response maximally flat. Why maximally flat? It can't get any flatter. Alright? And in which case, the magnitude response simply becomes mod h of j omega the whole square. If 1 over qp square is exactly equal to 2, what happens to this term? 0. So what remains is just the fourth order term. So what you will get is omega by omega p the whole power 4. Does that make sense? So if I plot the magnitude squared response as a function of omega by omega p at exactly omega by omega p equal to 1, what happens to mod h? It becomes half. At the origin it is flat. Mod h square, sorry. 1 by half, or 1 by 2 rather. For q p equal to 1 over root 2, the 3 dB bandwidth of the filter is omega p, right? And such filters where the response at DC is as flat as is possible, such filters are called maximally flat filters. Also called Butterworth filters, after the British engineer who invented them. You understand? So you can see that the filter characteristic tries to hug this flat line as much as possible, but eventually it has to go down to 0. So it does its best and then kind of droops off. So if you wanted it to stay flat for a longer time before it dives down suddenly, that's what you want. An ideal filter must be, the response must jump down very, very sharply so that you will be able to discriminate to closely spaced tones. So any suggestions on what I could do to make this even sharper? Higher on. Okay. So with this I will stop today and